So, if you don't know me, you'll know me, but I am Toby. I am today presenting sort of a spotlight on recent digital performance optimization using a Sparse EKF update. And also this is meant as sort of like a very high-level software performance optimization how-to if you ever find yourself wanting to speed up an algorithm that you're working on for use on flight hardware. This is also similar to Jeff's, a very informal meeting, and not meeting presentation, informal presentation, and I do not have slide numbers. So if you have questions, feel free to interrupt at any time because I don't have, apologies, but I don't have a way for you to easily reference the slide. So, okay, some context. This was a thing I did on Tuesday on a whim. I was not planning on giving a presentation this week, but I did this on Tuesday. It took about 3 hours. And I thought that the result was cool and the process might be useful to share. So now I'm here. Hopefully this presentation will teach you something about making software faster, especially flight software in C++, and detail a neat software performance optimization in DiGiTaL. Reminders, some motivation. Onboard algorithms enable spacecraft autonomy. Faster algorithms mean faster reaction times for our spacecraft, and faster reaction times can reduce risk in novel missions. The right answer, too late, is not useful. So if we have a great algorithm that can produce really optimal outputs, but it can't do it fast enough for the control frequency or measurement frequency that we need, it's not useful. In case you are not familiar with DiGiTaL, that's fine. This presentation is not focused on DiGiTaL. All you need to know is that it includes an algorithm that is computationally expensive. And the goal for the Visor's mission, this is a goal that I've kind of set based on the computational resources that we have and frequency of incoming data that we have in the Visor's mission, is that I would like this algorithm to run in 4 seconds. Pre-Tuesday, we had it around 5.1 seconds, and these are predicted numbers on flight hardware. On our computers, it runs much faster, but on flight hardware, 5.1 seconds. It now runs about 1 second. And worth mentioning that before the beginning of this year, it would have been around 25 seconds using the existing state of DiGiTaL, which is why previously we were planning on having to downsample our measurements significantly, but I think we won't have to do that, so we'll be able to process a lot more data. Okay, with that, well, we'll jump straight into kind of the technical bits. So, how to optimize software, my 2-step process, and this is key high-level takeaway that I would want to emphasize in this presentation. First one is identify the slow parts, and the second one is make them faster. And this is a very, there's an important subtle point in this 2-step process, which I think is easy to miss a lot of the time in trying to optimize software, which is this one. If you take a component of your software and make it 100 times faster, but that component of your software was only running 1% of the time, you will have improved the performance of your system at most by 1%. If you take a piece of your software that was running 60% of the time and you make it 8% faster, you'll have made a much more significant increase to the overall performance of the system. So this is really the key part. And I think something that is not super common knowledge of how to do a good job of, so that's part of this presentation. How we measure the performance of an existing system for software development in a way that's actionable and optimizable. And the tools to do this are something called CPU profilers. There are 2 that kind of work out of the box on Mac and Windows C++ development. If you're on a Mac, you will use an application from Apple called Instruments. And if you're on Windows, you'll use an application called the Windows Performance Analyzer. These are both made by the OS vendor themselves. So these are just default tools from Microsoft and Apple. You can get third-party ones too if you want. I'm on a Mac, so I'm using Instruments. And I ran the digital simulation C++ program that we've been using for simulating DiGiTaL in Instruments and captured a trace, and you get something that looks like this. So the overview of what this is, there's a sort of timeline at the top that's not that interesting to me, but you can see how CPU usage changes over time if you want to. It's pretty consistent for us because we're just running as fast as we can. you get a bunch of stack traces, which is a nested layout of all of the function calls that your program runs through while it's running. And you can pop in and out of these and explore them. There's many more down here that I have collapsed. But you also get a view of how much of the time your program spent inside each of these functions. So you can see at the top level, sort of the main function of your program. We spent pretty much 100% of the time in the main function. That's what you would expect. Ultimately, you can drill down and see what parts of your program are taking up significant pieces. So once we get inside DiGiTaL, you can see that 95% of the whole simulation, this is including DiGiTaL and the truth side, ground truth simulation, DiGiTaL accounts for about 95% of that. Within that...
Excuse me, Toby, I did not understand what you just said.
Yeah.
The truth part, is it included here?
Yeah.
So, so you are profiling at the same time...
The whole simulation.
Okay.
Yeah. And we could isolate this, right? We could just say, I only want to look at the subset of this stack frame and then see relative percentages. So these percentages are the entire simulation, ground truth and DiGiTaL. And I'll focus on these kind of 4 lines. You can see we have 2 functions called do graphic update and do SDCP update, which are 2 kinds of measurement updates that we do in the filter for DiGiTaL. And collectively, they account for about 83% of the CPU time of the whole simulation. But more than that, there's a single function, which is this kind of primitive scalar measurement update in the EKF that we use, that both of them call repeatedly. And we spend basically the entirety of the time doing the measurement updates inside this scalar repeated EKF measurement update. So this is kind of the ideal case for optimizing the system. If you find that you have a single function, hopefully something relatively small, that is accounting for a majority of your time. Because if you can speed this up by a factor of 2, a factor of 5, you'll get you'll get significant performance improvements on the whole system. So we can go look at what this function is, and it's 3 lines. This is the offender in our program. It's a short function, but obviously has a lot going on in it, but it is ultimately just a Kalman measurement update. And we can quickly try to get a look at what might be using up the time here.
Using the Jordan form.
Yes. Yeah. So for context, we have a 68-dimensional mean vector in DiGiTaL. This may change, but right now it's 68-dimensional. We have a 68 by 68 covariance. These are fairly large matrices. Not ridiculous, but they're fairly large. And we get as an input to the measurement update the state measurement sensitivity vector. It's a vector because these measurements are scalars, so each independent measurement is a uncorrelated scalar. And I'll look at the kind of dense operations that we have going on here. We have 2 matrix-matrix products. These are on 68 by 68. 2 matrix vector products. We have some vector outer products. These are all 68 by 68. 1 dot product and a scalar vector product. If you want to classify these into badness, there's sort of, I went through them in order of decreasing badness. Matrix-matrix products are the worst. For the most part, they'll be cubic in the size of your inputs. Vector-vector operations or matrix-vector operations, maybe n squared in the size of your inputs, and scalar vector or inner product operations will tend to be linear in the size of the inputs. So if we have 68-dimensional state vectors, we can expect that anything in the sort of the third category will be taking about 68 times longer than anything in the second category will be taking about 68 times longer than anything in the first category. So this is the one to focus on. Obviously, this is a simplification also. There's more operations in here, additions and subtractions. They tend to be a little faster, but they're definitely not free. So, but as a starting point, it's useful to focus on multiplications. Okay, so that's identifying the slow parts, making it faster. You can't always make your code faster. In this case, there was a saving grace here, which is that this 68-dimensional sensitivity vector C in practice has 6 to 8 non-zero elements. It's largely zeros with a very small number of actual significant values in it, and we know which positions in the vector these values occur at ahead of time. So, thank you. problem structure. Let's exploit it. So taking advantage of sparsity in software, you want to skip multiplications by 0 because you know what the answer is, and you want to skip multiplications by 1 because you know what the answer is relative to the input, and you want to skip additions with 0. So when I took a look at this function, saw that it was sparse, again, this was all just like, I did this Tuesday morning because I was procrastinating on other work that I was supposed to be doing. I kind of decided, okay, here's what I'm going to do. I'm going to restructure the function to see if I can emphasize the computations on possibly sparse values, kind of factor those out, look at all the operations that we're doing on those sparse values, and see if I can specialize the implementations that we have of those operations to take advantage of that sparsity and skip over things we know are 0, skip over things we know are 1. So first step, just to give you a look at the things that I did to this function to sort of prepare it for replacing these operations. There's a few standard transformations that I like to do on a function if I'm going to start trying to make it run faster. The first one is common sub-expression elimination. So if you ever see something that's computed the same in multiple places, just pull it out. Often the compiler will do this for you, so you don't have to always think about it, especially something simple, but if you want to know for sure that it's not wasted work, just pull it out into an intermediate quantity. So I did that, I called it F, F doesn't mean anything. We have another common sub-expression in this outer product, I pulled that out. Now this thing, I wouldn't say there's a standard restructuring that I would do on an expression like this, but because I know I'm aiming to eliminate sparsity, I'm aiming to eliminate operations on sparse values, the identity matrix is not ideal because that's a very sparse matrix. So there's going to be a lot of additions by 0, and if we can just factor this out and combine the multiplication by identity matrix into the original value, that might be desirable for us. So you can just factor out this multiplication in terms of the additions, and you get this. So great. From here, you actually get a new transformation you can do, which is just turn this into an in-place increment rather than computing the sum of the covariance matrix. You can just say, we'll increment it in place, so you don't have to allocate any new memory. That's nice. This one, looking at these pieces of the expressions, not super useful on their own, but in this case, because we know that P is symmetric, it's a covariance matrix, we can replace P with transpose of P and move it inside the transpose. And now we have some more common sub-expressions that we can eliminate. So we can now pull out these Kc times P's, make that a common variable. And that, I didn't see anything super obvious to do from there. So I said, okay, let's see what we can do with sparsity in this form. To look at what operations might now be sparse and be ripe for optimization, we can see that this, assuming C is sparse, this product is now a dense matrix sparse vector product. So we would probably be able to just take the subsets of the columns of the matrix that we're actually going to multiply by. The inner product, same thing, though dot products are really cheap, so not really worth spending too much time on. We have an outer product of a dense vector with a sparse vector. This can be optimized, but you actually don't need to change the form of the outer product at all, depending on the representation used for sparse vectors. So I'll get back to that in a sec, but I can leave that the same. I'll be able to leave it the same. And we have a product between a sparse matrix and a dense matrix. And again, because I'm going to be specializing these operations for the sparse form, I at this point also saw, you know what, I can just turn that P into transpose of P, because P is symmetric. And now I can specialize the single operation for multiplication by the transpose of a dense matrix. So that just allows me to use a shared specialization routine for both of these things, rather than writing two different versions or figuring out how to incorporate transpose into the sparse operation. So those are the three things that I might want to try to implement sparse versions of. What does it look like to implement a sparse linear algebra operation? First, you kind of want to look at how are you going to represent your sparse thing. There's a few different ways to do it, but generally you want to take the thing that has a bunch of zeros in it, get rid of all the zeros, we don't want to do operations on zeros, and just store the non-zero things along with the positions of where they occur. So we take a long vector with a lot of zeros and turn it into a small vector that we'll actually do our operations on. and some tracking for what indices do they match up to in kind of the real state space. So looking at those three operations that we identified from before and wanting to make them sparse, we can propose just like, okay, let me just try to come up with 3 routines that I'll use to do operations on these sparse values. So they're not the most prettily named things in the world, but I said I'll make a routine for multiplying a dense matrix with a sparse vector, a routine for dot product between a dense vector and a sparse vector, and a routine for multiplying a sparse matrix with the transpose of a dense matrix. And side note, for depending on the memory order that you use to store matrices, it's actually, you'll tend to get better performance from doing a multiplication of a matrix with a transpose of another matrix rather than a matrix with just another matrix. So if you can structure your program into matrix times matrix transpose, you may be able to get some kind of free performance from that. I won't get into why in this presentation. So having those, we can just kind of go and substitute them in. So we'll modify the interface to this function to also accept that list of indices. So we'll take a small vector and a list of indices. We'll replace this matrix vector product with the dense matrix scaled sparse vector multiplication routine. We'll replace this dot product with the dense vector sparse vector dot product. And we can skip the outer product, as I said, because C is now a small vector, but you can use the same outer product routine. You'll end up with a sort of sparse column matrix as the outer product. And we can use the sparse matrix dense matrix transpose to replace those matrix multiplications. And so that is the transform function, just referencing these 3 new helper functions for doing the sparse operations. It does make the function more complicated. It was simpler looking before, so there's a bit more complexity. This is a cost that you incur in the code base. But as long as you don't do this everywhere, and you say, you know what, this was a hotspot in our code. This was 3 lines of code. I can turn them into 6 lines of code, and it may have significant performance gains for us. I think it's worth it.
In this form, I would not be able to say that it's the chosen formulation.
Yeah. Okay, I'll add a comment. So having done that, we can go measure it again. So I will run this again in instruments. And we can see that the percentage of time spent in the measurement update has been reduced to 17% of the total simulation. It actually would be even lower than that because there's some external factors. I did not run these experiments in exactly the same way. So this was not a controlled comparison. This number should actually be even lower. But importantly, we've gone from about 20.5 seconds spent in measurement update to about 1.2 seconds spent in measurement update across a identical simulation, which is on this function alone about 17 times faster. On the whole, this has sped up the kind of core computationally intensive part of DiGiTaL by about a factor of 4. And that's because this wasn't the entirety of DiGiTaL. And for the sake of us running simulations, it also has sped up our overall simulation by a factor of 3 to 4. So it allows us to iterate a lot faster. We don't have to wait for things to run as long, which is nice. Conclusions. Big performance gain for DiGiTaL. It did not take me that long. Like I said, this was a procrastination project. And the key takeaway for doing software optimization that I would want to emphasize, if you ever find yourself needing to do this, is if you really want to look at performance, measure first, identify the hotspots. DiGiTaL is a 10 to 15,000 line code base. I spent 3 hours optimizing 3 of those lines. You don't want to spend 3 hours optimizing every other triplet of lines in the code base when most of them are not going to get you anything for it. So spend your time on the things you know are going to be worthwhile, and that's why I really want to emphasize the value of profiling tools if you're really wanting to make an algorithm fast on hardware. That is the end.